Our speaker this evening has over 20 years of industry experience, and he is the VP of Solutions for Splice Machines. Please welcome Eric Kalabacos.
Thanks, folks. Fun to be here on a rainy night in Manhattan. Thanks to all of you folks that made the effort to get here. I was afraid, seeing what the weather looked like today, nobody was going to show, so I appreciate it. I hope it's worth your while. I probably don't need to say much more. You guys seem to know, a lot of the key points from the little quiz that we did. But anyway, just briefly about myself a bit more. I've been with Splice Machine pretty much since we started, late 2013. Have worked in mostly in Silicon Valley in the last 10 years here on the East Coast, and technology companies, a lot of big enterprise application companies before getting into the database world and the big data architecture world that Splice Machine plays in. So I'm just curious, before I jump in, just to get a little bit of a feel of kind of where people are coming from here. Who considers yourself like sort of a DBA, database administrator type? Get a few feeling that. How about developers, people that develop apps that are database driven? People with experience with the Hadoop ecosystem. Okay, so a good smattering of folks. That's helpful. It's helpful to get a little bit of a sense of where everybody's coming from. So as you saw on the website, the kind of theme of our talk is this concept of Lambda-in-a-Box. We'll be talking about what that means as we dive into the talk. But essentially, what it has to do with is that Splice Machine has built an RDBMS, relational database management system, that is really designed to handle both operational and analytical workloads simultaneously within the same architecture. And we'll be talking about how that relates to the concept of Lambda, and a lot about how we do that, why we did it, etc., as we go through today's talk. So Keith, talk a little bit about sort of how we founded Splice Machine, a little bit of background, where we came from, and why we built the product we have. Our CEO, Monty Zwiebin, went to CMU and has been an entrepreneur in Silicon Valley for the last couple of decades. He sits on the Dean's Advisory Board at the CMU, that's Carnegie Mellon Computer Science Department, where he got turned on to Hadoop and MapReduce maybe 6 or 7 years ago. The dean there was really emphasizing that with students going through the computer science program at the time. Monty's background was in AI, and like me, had been involved with a lot of application companies that both had operational sort of OLTP style components to the software, and also heavy-duty analytical or machine learning AI-oriented capabilities in the software, and always had been challenged with the scalability of the database platforms that these applications ran on. And when he learned about Hadoop and the way it had sort of begun to democratize massively parallel computing, distributed architectures, which prior to that were really the realm pretty much of computer science PhDs, technology and open technology that had made it possible to deal with extremely large amounts of data in a relatively cost-effective way through a scale-out approach. He got very excited about that, but he realized that if you really wanted to try to use Hadoop for traditional database-driven applications, it was very difficult to do. There were So as I was saying, when looking at the tremendous promise and power of Hadoop, he also realized that to really be able to leverage it, and for a lot of, if you think about most of, especially our focus initially was mainly on the operational side of things. If you look at most of the operational applications out there in the world, whether they're driving websites or order management systems or CRM, ERP, all these common use cases, that they all run against SQL databases, right? And people are very used to developing applications using SQL. I imagine, given the fundamental nature of this meetup, that you guys understand that very well. Probably all people that work with it in one way or another. A simple declarative language that is extremely ubiquitous. We felt that to bring a true SQL relational database to the Hadoop world and to be able to leverage the scale-out capabilities on commodity hardware that is at the core of Hadoop's value proposition in a way that makes it relatively simple and easy for SQL developers to develop new applications, and also importantly to be able to port existing SQL-based applications to a scale-out architecture without having to do like hardcore application rewrites. This was really kind of the initial vision of what Splice Machine was about. So providing full-blown ANSI-SQL in a transactional model so you can run OLTP-style applications, combined with scale-out and the associated cost advantages, and to be able to do things extremely fast. Initially, the product was based just on Hadoop, and as you'll hear as I go through my talk, specifically HBase in terms of our storage layer. We, in the last year, we'd actually been working on this for about 3 years, have integrated the Spark compute engine. Who here is somewhat familiar with Spark? Can I get a show of hands? Okay, about half of you. Which has a lot of momentum behind it. Particularly, we brought in Spark because our ultimate vision was to power not only OLTP applications, but to be able to power heavy-duty analytical OLAP-style workloads, machine learning workloads, etc., simultaneously. And we feel that with the combination of these two very powerful technologies and the simplicity that we bring to it through delivering it as a typical SQL relational database like a MySQL or Postgres or SQL Server, Oracle, that it would really be a way to put this kind of power in the hands of many more people. Just a little bit about how we kind of talk about Splice Machine from a marketing perspective and some key areas where our technology is being used. Certainly analytical tools have been around for a long, long time. Transactional applications have been around for a long, long time. But there's always been kind of this gap where typically the analytics that you're able to do are always somewhat behind what's happening in your transactional applications, right? You have to ETL the data over. You're often, especially with a lot of in these verticals, typically dealing with very large data sets. With the rise of the Internet of Things, the need to interact in as close to real time as possible, in as intelligent a way as possible, the requirements for being able to act on data in an intelligent way in closer and closer to real time continues to grow. And so, if you think about things like healthcare, where you might need to respond to patient monitoring system, right? When they're in a hospital and then the system identifies they're at risk of a sepsis infection, or in financial services doing fraud detection when somebody swipes a credit card, it needs to happen relatively instantaneously. In digital marketing, where you have to determine which ads to serve to a potential customer on a website. In supply chain, where you have to track in real time where physical inventory is and be able to optimize the logistics of your supply chain. These are all fields where there's more and more pressure to be able to deliver intelligent applications that can actually take action on something in the moment. Can we hold off on questions until the end? Is that okay?
What is Spark?
What is Spark? Let me save that. We'll talk. We'll have a slide on it, so it'll make sense when I get there. So these are a number of fields and types of use cases that our technology is well suited for. So as I was saying, this imperative for data to be very recent, but also to be able to have deep history of data so that you have enough information when you're trying to make intelligent decisions in your applications, that they are that there's enough data to really have enough signal that you're making the right decisions. And with some webinars that we've done, we've actually interviewed hundreds of IT executives to just find out sort of where they're at in terms of the data that they're able to use in their analytical or machine learning applications, and be able to then make use of it in how they interact with customers or patients or whatever. And we basically found that 75% today still are dealing with data that's at least a day old, if not more. Some are being able to act on data within hours. Maybe about 10% are doing stuff in real time, and that there's a tremendous desire, especially in these industries, to really be moving towards this vision of acting on real-time data. So what's one of the main reasons why traditionally you have this lag? If you think about most traditional IT shops, they're typically made up of a set of OLTP applications, a set of analytical applications, whether they're data warehouses, data marts, tools for just running standard business reports, heavy-duty ad hoc analytics, machine learning, etc. And because of the requirements around what the different types of applications require, the data typically has to be moved between these systems through typically costly and complex ETL processes, right? Whether you're using products like Informatica, things like that, to move the data from your Oracle-based applications to your Teradata-based data warehouse, as an example. So in recent years, with the advent of a lot of these newer technologies like Hadoop and Spark and a lot of the related technologies, there's been an approach that has been growing in momentum as a way to try to minimize this lag of ETLing between your two environments. And that has come to be known as the Lambda architecture. Who here has heard of the Lambda architecture before? Okay, maybe about a third of folks. And you could easily do spend a whole hour talking about what the Lambda architecture is in detail, but put very simply, the idea of the Lambda architecture is to integrate different compute engines that are optimized for different types of workloads together so that they can be acting on a large data set and simultaneously be bringing in very recent up-to-date, near real-time data, and kind of merging together the batch type of processes that are required against big data sets with very recent streaming data, and then being able to both analyze it and do something with it in as near real time as possible. Traditionally, Lambda architectures are broken up into three main layers: the batch layer, the speed layer, and the serving layer. So you can imagine, let's just say it's an ERP system, and you're tracking tons of inventory location data. You've got tables, say with billions of rows in them. You need to be doing aggregations and other analytical type of workloads on that data. That's the type of work that would typically be happening in the batch layer of a Lambda architecture. But then you're also streaming in the latest data from the RFID tags on your inventory, and in order to say predict, or an application that might serve up, when a package is going to be delivered somewhere or something like that, you might need to be looking at both the very recent data, which would be coming into your system through what's called the speed layer, merging together computation done in these two different layers to produce a result that could then be served up to some type of real-time application. So in a way, it's kind of like a duct taping different technologies that are optimized for doing these different types of workloads together without having to duplicate the data and replicate it as you would in the traditional model that I was depicting in the previous slide. So these particular technologies that you see here are just examples. Lambda architectures have been built using a lot of different components. In our case, we're talking about Hadoop and MapReduce here for the batch layer, a streaming technology like Storm and Kafka to handle the real-time data ingestion, and some type of key value store, maybe NoSQL database for serving your applications. And you could plug and play different technologies. HBase is by no means the only technology that you could use for the serving layer, etc. But to do this, it's complex, right? You have to essentially worry about how am I going to integrate these different components together so that the whole system works in an efficient, integrated manner. So really what we've tried to do with Splice Machine is to essentially give you this Lambda architecture all pre-integrated for you that you can then just work with as you would a traditional SQL RDBMS. And we'll be talking about how we did that as I go through the talk. In our particular case, as I mentioned, at the outset, key technologies that we have integrated are Apache HBase, which is really our storage layer and is a very efficient engine for doing lots of small concurrent reads and writes. HBase by itself is a NoSQL database, so it can be challenging to use if you're used to using a traditional SQL database, but it has tremendous performance characteristics for those types of jobs. Spark is primarily a distributed in-memory computational engine, originally developed out of the AMP labs at UC Berkeley, which is very well suited for executing jobs that require large amounts of data, lots of intermediate result sets. Like from a SQL perspective, you think about an OLAP-style query with lots of joins and aggregations. You have intermediate result sets to execute the query. Very efficiently architected for those types workloads. And then we use a combination of Spark streaming, which is a subset of the Spark ecosystem designed to bring streaming data into Spark, combined with Apache Kafka, which is a messaging system, a message bus system, similar for those of you who are familiar with traditional message bus technologies like MQ series from IBM or web methods, that type of technology. You can actually use pretty much any of those types of message buses to work with Splice Machine, but we do have pre-integration with Kafka out of the box. So this is, I think, a very easy to understand graphic that helps explain why we feel that our system is optimally suited for these mixed workloads. If you think about traditional database architecture where you're trying to run, say, big OLAP queries that take minutes or hours to run, and then you have a bunch of users that are using applications, running reports. You can imagine like a customer service department where it's important to get very snappy. Your screen's got to redraw right away. If you're waiting for seconds or minutes, it's problematic. Those of you that are running in IT shops know about the types of SLAs that you often have to deliver for those types of applications. And essentially what happens is the two types of queries, two types of jobs are competing for resources. The OLAP style queries are like the big 18-wheelers going at 45 miles an hour up the hill, and you end up with traffic jams. So what we've done is taken what to the developer or the application is a unified SQL database, and we figure out, based on evaluating the queries and the resulting explain plans, the jobs that have to be run, whether the queries are OLTP style queries, quick, I just need to grab a record even if it's out of a 100 billion row table, or do small range scans of data, reads and writes, queries that are typically expected to run in milliseconds in a lot of enterprises. So our architecture will figure out if it's that type of query or a costly query that's going to take some time to run, and we will automatically execute that in the appropriate engine with very easy to configure and efficient resource isolation, so that the two types of jobs, even though they're both going against the same data at the storage layer, are not getting in each other's way. So another way to think about that is, with a traditional database, if you're trying to do big OLAP style queries and OLTP at the same time, as your OLAP load increases, the response time on your applications gets slower and slower. And the vision of Splice Machine is that you can scale, and especially as a scale-out architecture, you can just add as many nodes as you need to meet your SLAs and get your job done with really no impact on your OLTP response times. So as Eric mentioned at the beginning, we made the decision at Splice Machine earlier this year that we were going to open source our technology. We live in a world, we leverage a tremendous amount of open source software already in our solution. As probably many of you know, Hadoop and Spark are open source technologies for the most part. We really decided that we wanted to be fully immersed in that new world, in that model, and open source the product earlier this year. We do have one of the ways that we actually make money at Splice Machine, we do have both a community edition, which is 100% open source. You can download it from GitHub and use it to your heart's content. It contains really all the fundamental elements of our system. You can run it at scale on a cluster as large as you choose. But we did reserve a certain set of features, mostly geared at large-scale IT organizations, things around the backup and restore capabilities, security-related capabilities, and a few other things we'll talk about as we go forward. And then, of course, like most traditional open source companies do, you also get our support and services with the Enterprise Edition. But it really is, I would say, 95% of the technology is available in the open source version.
Can you quickly explain in this context the virtual table interfaces? Are those views?
No, virtual table interfaces are not views. I do have a slide coming up on it, so I'll get into it in a little bit then. Do you have a question? Okay. Just a couple things about if you want to get involved and try the technology for yourself. First of all, if you go to our website, we have a community site. You can download the full clustered version. You can run on a cluster. You can also download a standalone version if you just want to play with it from a functional perspective that you can run on a laptop. And then we also do have a very easy to use sandbox you can run on AWS. You have to use your own AWS account, so whatever you just basically fill out a form, pop in your own EC2 credentials, and with a couple clicks and a few minutes, you'll have a full-blown Splice Machine cluster up and running that you can use for as long as you want. For those of you that are familiar with AWS, we basically do this using CloudFormation templates. You can actually grab the template too if you want to tweak it and do something more full-blown than just sort of a sandbox. You can use that as a starting point for setting up your AWS environment. So pretty easy to get access to the technology. We have on our community website, we have a Slack channel you can jump in on, and my team is great about responding to questions and comments there. We have a set of tutorials, both video-based tutorials as well as sort of step-by-step instruction tutorials with code samples. I mentioned before you can actually clone the entire open source code base on GitHub. So definitely anybody that gets excited about this, you're interested in trying it, you feel like you're interested in contributing to the product, we're very interested in talking to you. So enough of that sort of marketing spiel here. We can start jumping a little bit more into the guts of the system and how it really works. So we leverage really three main open source projects in building Splice Machine. We really felt from the beginning that it did not make sense to try to build a system this complex from scratch, and we spent a lot of time analyzing different open source technologies that are out on the market. So first of all, for our SQL support, rather than building our own SQL parser and executor, etc., we started with a technology called Derby. Derby is essentially an RDBMS written in Java. It's been around for, I don't know, at least 15 years or something like that. I think it was originally developed at Informix. It ended up, when they merged with IBM, owned by IBM, and then they open sourced it. So it's an ANSI-SQL 99 compatible database. pretty lightweight in terms of the code base. It's good for mobile apps. In fact, every Android device has it embedded in there. It's used often as a sort of, if you need some SQL database for mobile apps running locally. Written in Java, one of the things we liked about it, has ODBC and JDBC connectivity, so that that's by far the most ubiquitous way that most applications connect to databases. So we took Derby and essentially gutted the storage layer and replaced that with HBase. So HBase is one of the components of the standard Hadoop distribution. It's essentially an auto-sharded key value store. A lot of people will refer to it as a NoSQL database. One of the key things it brought to Hadoop, those of you who are familiar with Hadoop may know that the file system, HDFS, which is one of the key components of Hadoop, the files are immutable. So what HBase really brought was mutability to storing data on Hadoop. Under the hood, HBase is storing its data as files on HDFS, known as H files. We'll come back to that a little bit later. And we've seen HBase proven to be highly scalable. It's used, for instance, by Facebook. The entire messaging application on Facebook runs on HBase. So it has proven to scale into petabytes of data. So we really chose HBase for the auto-sharding capabilities and for its efficiency in doing high concurrency reads and writes. We'll talk about that a little bit more as we go on. And then the last one, Apache Spark, primarily an analytical engine. It's used a lot in, by data scientists these days. It's probably the area where it's gained the most traction. It's very fast because it does its work in memory. You do need, to really leverage it, you need boxes with a fairly significant amount of RAM to use it, but it does have great spill to disk capabilities. If data sets do get too large for RAM, to run it entirely in RAM, and it's very resilient to node failure on a distributed cluster.
You say you got the storage layer, but I guess you also have to do some changes there, because before you imply that the splicing decision is driven by the query plan, you have some sort of heuristic there, so there's some little changes.
Yeah, well, the storage of the data is not really, that happens at the time that the data is ingested into the system, right? And HBase has the ability to shard the data. Basically, a table in HBase gets sharded into what are called regions. The regions are typically, based on a certain range of data. One of the very powerful things about HBase is that essentially they call it a row key in HBase. For those of you with a more traditional database background, you can think of it as your primary key on a table. Data is sorted by primary key physically in the order of the key. So and then it's broken into chunks and broken up into regions across your cluster, automatically replicated. So if a node goes down, there's always additional copies of that data. And the HBase master node kind of knows which ranges of data are sitting on which nodes of the cluster. And because the data is sorted, if you have to get a range of data out of HBase, it's extremely efficient to do so. We do have to, when we execute a query, yes, we have to figure out where to, how to distribute that. We will get into the query execution model in a little bit. Let me just see how I'm doing on time. Okay, so we already talked about HBase a little bit. In the interest of time, I won't get into the architecture in a great deal of detail. Some of the key points I made already. It auto shards the data across the different nodes that are referred to as region servers in HBase. It has a memory store concept where data gets written to memory on a periodic basis. It gets flushed to disk and stored in these files on the Hadoop file system known as H files. HBase has a process known as compaction, where it continually on a sort of regular basis merges these files together as they grow and kind of cleans up the storage and does kind of housekeeping tasks to make it very efficient to run. So that's just a little bit about HBase. Spark, again, is primarily an in-memory technology. It's developed at UC Berkeley. Actually, the head of the computer science department there, Mike Franklin, that led the development of Spark, is on our advisory board at Splice Machine. It's helped us a lot with integrating the technology into our product. I already touched on a few of these key things, so I won't spend too much time on here. It's also a distributed architecture that automatically partitions the data across nodes, has a very efficient way of pipelining data sets. They're in a very resilient way. And there's a whole set of different libraries for things like machine learning and other processing intensive tasks out there on Spark, and it's growing very fast. So that opens up a lot of opportunities to use these types of tools on top of Splice Machine. So again, we have really integrated the two technologies together. We feel in a very unique way. A couple key things I want to mention, more technical things. So first of all, when you send a SQL query to Splice Machine and we parse it and we create an execution plan and resulting bytecode that's actually going to execute the job, and the same bytecode gets used whether the query gets executed on HBase or on Spark. Also, as I mentioned, really the persistent storage is all in HBase. But remember, we were talking about the vision is how can we do these heavy-duty analytical jobs without impacting our performance on the OLTP side, where we have very short response time. So we did, I think, something pretty innovative here. When we access the data, rather than going through the HBase, so let's say it's a query, it's an OLAP query, it's going to run on Spark. Now we need to get the data. We don't go through the HBase API to get the data. We go directly to the files sitting on HDFS. So there is no load on HBase really at all. The only thing is that there may be some very recent DELT data that is only in the mem store of HBase, hasn't yet been flushed to disk. We do grab any of those deltas from the mem store via the HBase API, but that's generally a small amount of data, and most of the data is coming directly from the HDFS file system. So here's just another, I think, view of our architecture. So first of all, for the Hadoop folks in the room, it's really a pretty standard Hadoop install. I know we mentioned on the quiz that Splice Machine runs on all three of the major commercial distributions of Hadoop: Cloudera, Hortonworks, and MapR. The components that you really need to run Splice from Hadoop are HDFS. We don't really use MapReduce at all. Not that you can't use it for other things on your cluster, but Splice Machine does not use MapReduce. So basically just HBase, the Hadoop file system, or MapR file system in the case of MapR, and Zookeeper for node coordination, and then Spark, obviously. So let's see here. I guess I'll just quickly mention here that the way we integrate Splice machines, but the Splice machine jar essentially sits on each one of your region servers. We interact with HBase via what are known as coprocessors. If anybody is an HBase geek in the room, you'll know what that is. It's essentially a technology for extending the HBase API. Very easy to deploy. If you use Cloudera, it's just deployed as a parcel via Cloudera Manager. It's a little bit more to it in Hortonworks and MapR, but still pretty straightforward. Just to talk a little bit about how we execute a query. Again, these are just standard SQL queries. It's full ANSI-SQL. I'll show a slide that has a little bit more detail on our SQL support. Essentially, ANSI 99 SQL plus some mostly Oracle-specific stuff we've added, and some other more modern things like window functions. But anyway, you issue a query to Splice Machine, whether it's from our command line interface or from an app via JDBC or ODBC or a SQL tool like Squirrel or something like that. We take the query and leveraging the Derby SQL parser, we parse it, generate a syntax tree, and then we have our own optimizer, part of our I think key IP that we developed at Splice that optimizes the query plan, figures out whether to go against base tables, indices, what types of joins to use, just like a traditional SQL optimizer would do. One thing I'll mention that was not easy to do, and I'm very proud of the work we've done at Splice Machine. We saw, especially with a lot of packaged applications, they often deliver very nasty SQL, because it's often not SQL that was written by a human being or really thought through doing it efficiently. You have these object-oriented applications, and people are dragging and dropping stuff, and it builds SQL queries, which often have a lot of subqueries in them, which are challenging. So one of the key things we were able to do is unroll any of those nested subqueries and essentially turn them into joins that can typically execute in a small fraction of the time that they would otherwise take. But anyway, key thing is we optimize the SQL, we generate a query plan, and then that generates one set of bytecode to execute the query. We have a statistics-based optimizer, so it evaluates what the cost of the query, and below it, whatever the threshold is, it will determine whether to execute that query on HBase or on Spark automatically. You don't worry about that at all as a developer.
Can you force it?
I'm sorry?
Can you force it to use
Can you
one?
force it? You can force it if you want to. And
Because if my analytic uses this application, I just want this application to always go to Spark.
Yes, and again though, it will, it typically would only be queries that are going to run sub-second response time type of queries anyway that the optimizer would typically send to HBase. But yeah, you can execute every query on one engine. I believe you can also configure the threshold in terms of the cost as to where it would.
And for given application, see, I know that this application always needs HBase. This application always needs Spark for the same database.
Yeah. So yes, my understanding is you can force a query to go on one or in one engine or the other. But again, we find that often where people get really excited about Splice Machine is where there are these mixed workloads, and they would like to be able to bifurcate and computation. We do, as a Hadoop-based technology, we essentially run on top of Linux. Typically, you are able to manage and isolate the HBase versus Spark resources in terms of memory and CPU, etc., which you can tune based on the load balance in your particular configuration. I won't get into, these are just some examples of areas that that you configure to do that. For the jobs that run in Spark, the longer running jobs, on top of that, you do have a fair scheduler that we can take advantage of in Spark, where you can set different pools of priority in terms of jobs running, and then different types of queries can be associated with those pools to help prioritize when there's contention for resources within just Spark itself. One thing that I feel is really exciting about our integration of Spark into our product is that Spark has really excellent job management and visualization tools. It's part of the Spark technology, and we took that and basically use it as a way to give you essentially kind of an explain plan on steroids for Splice Machine. I was really excited about this because in our 1.0 product, which did not yet have Spark in it, we were writing our own explain plan stuff to try to make something that's really sophisticated and powerful. Is not an easy task. But Spark gave us really excellent tools for analyzing how a long-running query is performing and how it's being executed, that we're able to kind of plug into. So when you execute a query on Splice Machine, you can see all the different jobs. These are different types of joins and sorts and things like that. You can see graphically which jobs have to happen serially and which can happen in parallel. So as an example, these jobs here can both occur in parallel, these stages, before moving on to the next stage of the query execution. I know this is a bit of an eye chart, but you can, here's kind of a little bit of a drill into a couple of those stages. So you can see how we've, if you look at it at an execution plan in Splice, your SQL will be broken down into these types of jobs, and you'll see here in detail how they're being executed. You can drill into each of those. This is just drilling into one stage and see, for instance, things like, how much of the time for the query is taken up serializing and deserializing the data in the scheduler, reading and writing the records, garbage collection, etc. So very powerful for analyzing and tuning performance of OLAP queries. We're trying to make Splice really be a good cluster citizen, if you will, in terms of interacting with other technologies, other data sources, other query engines, etc. So some key things we've built in Splice. First of all, we have a virtual table interface that lets you access either external databases or external files as if they were tables directly in Splice Machine. Once they've been mapped via the VTI, they're essentially treated as first-class tables in the database, even if they're not actually that. Those files could be residing on HDFS or even on the local file system or something like S3. Someone had a question about the VTI on this side. Did that answer your question, essentially? And also we have a sort of MapReduce IO format to be able, we can register Splice tables in H catalog so that you can query data from other query engines besides just Splice Machine. I'm very proud of our SQL coverage. I think we definitely have the best in class in terms of SQL on Hadoop technologies out there. I mean, first of all, we're a full read and write engine, full CRUD operations. A lot of the SQL on Hadoop technologies are more read-only. It's evolving, but still they're primarily that way. I'll get to you in just one sec. Again, we were able to do this because we really leveraged Derby and its SQL support. Question?
A year ago, I tried to run TPC-DS on Hive and SparkSQL, and they could only run about half of the queries.
Yeah.
Are you able to run?
Yeah, we're basically running the full, I don't think we've done DS, but we do run the full TPC-C and TPC-H benchmarks. And one thing we're really excited about, we're planning to release soon, is Simultaneous Benchmark, where you're running both TPC-H and TPC-C. And in fact, if you download, we have it set up, we have a nice way that if you want to try it yourself, you can actually, using, I think it's JMeter, the tool for doing it, a way to automate actually easily running those benchmarks on Splice Machine.
What's timestamp and what's granularity? I don't see that.
So the question was about timestamping and our granularity on that. So first of all, HBase itself is a timestamp-based architecture, right? All the operations on data, everything is just writing new versions of records with timestamps associated with it. And they're very, I don't know how, they're very granular. Something like that, millionths of a second or something like that. And we make heavy use of HBase's timestamping when we talk about our MVCC model. I have a slide coming up on that, but we have a snapshot isolation-based MVCC model that leverages those timestamps. Does that answer your question?
Pretty much. So the timestamp should be
It probably should be on there this is not 100% everything. It's just trying to give an idea of key stuff. You know, one thing I will mention, I mean, a lot of people when they think about big data technologies, they're thinking about unstructured data. While you can store blobs and things like that in Splice Machine, and while you can also access data that's external to Splice, as I mentioned, we are primarily more of a typed data database, like a traditional SQL database. When you create your columns, you specify the data types, etc., and it works in that way, very much more like a traditional.
Would you be at some point supporting searching into JSON records? Some SQL says, "Oh, I'll just treat this like it's regular for search purposes."
Yes, we are actually looking. We don't have what I call native JSON support yet, but it is an area that we're working on that we do intend to deliver. I'll also touch on. I don't think it's in the slide here, but I'm really excited that we are also adding vertical columnar storage formats to Splice Machine. It's going to be coming out in a matter of weeks, where we're supporting both Parquet and ORC to the two most popular columnar forms. Let me just get this.
I'm not sure if you have another slide on this, but what do you have from ACID?
ACID, yeah, we will get to ACID.
Okay.
Yes, I do.
Is that only going to be enterprise, the column stores?
No, not to my knowledge. I shouldn't say 100%, but I'm pretty sure it is not.
on the original breakdown.
Yeah, and the idea too is that you'll be able to access, say, Parquet files that either are just sitting on the file system because they were put there by an external technology, or you'll be able to say in Splice Machine, this table, I want to have a Parquet representation, a columnar representation of the data, so you can do that, on a periodic basis and run jobs for which columnar is optimal for fairly efficiently. Sorry, this thing came up. So just a couple more things I want to touch on this slide, and you can kind of read a lot of it for yourself. I think key thing is it really is full RDBMS functionality. Primary keys, foreign keys, constraints, triggers, transactional semantics like commits and rollbacks, UDFs, views, join. Those of you that are familiar with a lot of the SQL on Hadoop technologies, a lot of this stuff is missing from a lot of those technologies.
UDF, is that permitting binary from an external language?
I think they have to be just
Like
written in
Java.
Java. Yes. I will be talking about, we have just announced added PLSQL support. That's still not a function, really, but more like for stored procedures anyway. You'll now be able to do them in Java or for PLSQL. Not that we expect too many people to write new PLSQL, but for people that are looking to port applications that were written for Oracle, will natively support PLSQL, which is, I think, a unique thing about Splice Machine in the Hadoop world that I'm pretty excited about. We know what a challenge it will be, but to replace Oracle, and I don't expect overnight companies are going to do mission critical applications, but they're looking at opportunities to do this, and we feel that ultimately can be a really great market for Splice Machine. In terms of our joins, we've optimized the join strategies for a distributed architecture. We take great advantage of the fact that the data stored in HBase is already sorted by key. So like in a lot of cases where you might normally have to do a merge sort join, we can pretty much skip the sort step, right? Which can allow those types of, it won't always happen depending on if the data's got to be sorted the way the query is written, but it can often be very efficient for those types of.
As long as the primary key is involved.
Exactly.
Very, very quickly. So anything that's supported by Derby, you guys have an extended Derby.
We have extended Derby somewhat. For instance, Derby does not have window functions.
Okay.
We've got something like 20 window functions. We've added a few, mostly Oracle specific. It's mostly been driven by customer requirements, but it is our goal and our intent to build on Derby. Derby we really see as our starting point, and we definitely have added some important things like window functions, and again, mostly some stuff that is specific to some other popular SQL databases. Yes, there is, in fact. I mean, you can do it because of the fact that everything is time-sensitive. He's asking if you could do like an as-of type of query.
Right.
What would the results of this query been if I ran it 2 days ago? Type of. I think so. Yeah. I mean, because again, when it's a complex query, we're leveraging Spark, right? And so we really do feel that I think there's a slide coming up, but I'll just mention it here. It's probably worth mentioning it. Indexing. So if you do have known access patterns for your data, one of the things that I think is unique about Splice in the SQL on Hadoop world is you can do secondary indexes. Under the hood, our indexes are basically just additional HBase tables. So you can basically have your data sorted as many different ways as you need to by using indexes. I will give you a caveat, and this is one area why I'm excited about Parquet. If you're dealing with queries that are they're big OLAP queries, they're scanning a lot of data, and they have to return really large data sets. Like the actual data set returned by the query is many millions of records, let's say. Because of it being a distributed architecture, you can have cases where if your index does not cover all the columns that you want to bring back in your result set, where there can be a fair bit of cross-talk, network talk between the nodes, which has a performance impact. So for those types of queries, we generally recommend doing covering indexes, so you include all the columns that you expect to return in your result set. That's not needed if you're talking about queries that are only going to return, in the thousands of records. It's fast enough. But for ones that are, and therefore, if you don't always want to think about that, having a columnar representation can allow you to run a lot of those kind of queries without worrying about covering indexes. Any other questions about SQL coverage?
Can you make an index on the join?
Can you make an index on a join in the process of doing the query, or you're saying just to?
No,
Yeah,
I want
sure.
because in regular SQL I cannot do it.
Yeah. I'm not 100% sure, so I don't want to answer the
Because
question.
it would be a feature I always wanted from SQL. Sometimes you always want to do this join. And I want to create an index that will do a join beforehand for me and just return the data when I need it.
Yes, I'm not sure. I'm not 100%
So
sure.
other than like a query, database table, and view triggers, other than it can allow to create the report like that we create in a SQL, like SSIS, SSAS, and SSRS, like analysis services, integration services, and reporting services. Is that facility is in the
Essentially, yes. You're talking about like the Microsoft SQL Server
yes.
utilities, right?
Yeah, like in a SQL we do that the SSR means in the new 2012 and 2014 we do that the analytical services and SSRS and SSAS, analysis services, integration services, and reporting services.
Yes.
So that kind of the features is allowed in this product because yes, I see that there are some very good benefit about the primary key and foreign key that constraints. Here it balance that. Referential integrity and all those things, I see that. And other than like joins, triggers, DML and DDL, all that functionality, I see that. But I am not 100% sure about these SSAS, SSRS like that. So the latest that more popular in our industry.
Yeah, I would say I know that we've integrated SSIS with Splice Machine. I'm not entirely sure about all of those technologies. I would encourage you, you can join our Slack channel and ask questions on there. We have, all our developers are on there. I'm sure somebody could answer the question in more detail than I can, if you would like. How are we doing on time, Eric? Are we good? Okay, we're getting close. I might have to race through the slides a little bit. We did have a question about ACID, so here's a good sign. Eric encouraged me before I'm going to walk over to this side of the room, which I realized I haven't done yet, and hang out with you guys over here a bit. First of all, Splice Machine is fully ACID database. It has been so since the outset. It was a fundamental part of our vision to deliver a database with ACID properties from the outset. For anyone that's not familiar with the acronym, it really boils down to the capabilities you need to run a transactional system. The A atomicity, it has to, if you're doing an operation on the database, it's an all or nothing thing. It can't be left in an indeterminate state. Supporting lots of concurrency, et cetera. I won't go into all the details of it, but that's essentially what it's about. There are a number of different ways to provide ACID support. They're generally broken into different classifications of what's called MVCC, or multi-version concurrency control. There are different levels of that. Splice Machine implements the level known as snapshot isolation, which is a fairly standard in traditional databases like Oracle. This was a really key part of the IP we developed at Splice Machine. We actually leveraged work that Google had done to provide ACID semantics on top of Bigtable, which is their distributed key value store, and also a project called OMID, or OMID, O-M-I-D, at Yahoo. Yahoo is where Hadoop and HBase, where these projects began, and they did a project to provide ACID properties on top of HBase, and actually the key person behind that has been now one of our chief scientists at Splice Machine for a number of years, and so we built on that work. It's an area we're very proud of, our snapshot isolation system. It's fully distributed. HBase itself does provide row-level ACID semantics, but we've extended that to multi-row, multi-table ACID semantics, so you can really do the types of transactions you'd expect to be able to do on an OLTP database. Just 1 second, I want to get this guy's question. Well, I do know that our database is a strongly consistent database. It's not eventually consistent. I'm not sure I fully got the details of your question.
Basically saying that it goes to memory and then gets flush disk.
Correct.
So is it considered a done transaction if it's on memory on 2 nodes, or are you waiting until it goes all the way to it's done all at HBase node?
I believe it has to go all, well, I'm not 100% sure, so I don't want to answer it out of turn. Again, happy to take the question and get back to you, and you can also certainly hop on our community site and ask it there. Okay. Yes, sorry.
So one of the biggest problem for NoSQL, unless it's specifically is a counter problem, is like an update A equal to A plus delta. Do you do it? Can I guarantee that this delta won't be applied twice? Do concurrent updates?
My understanding is absolutely yes. And again, in terms of how, it's a little bit beyond my level of knowledge of the guts of our MVC system, but certainly there are folks, our CTO, other folks at Splice can answer the question at whatever level of granularity you like.
Usually NoSQL do not have logs. You need select for update to do this.
Anyway, I'm pretty certain that the answer is yes, that we do it. So just really quickly, I know we're out of time here. I'll just wrap up. One thing I think I just want to cover briefly, because I think it was in the abstract that we gave for the talk. We have actually done some benchmarking against other well-known SQL on Hadoop technologies, particularly on HBase, SQL on HBase technologies, notably the Phoenix and Trifodian projects. And we're out of time, so I won't go into all the details of the differences between the systems. But I think key thing is our Spark support, the fact that when we run heavy-duty queries, we're going directly to the files rather than going through the HBase API. Also compaction, one area that people sometimes have issues with HBase for an OLTP application that requires very tight SLAs, very short response times. You have this compaction job that HBase is doing what are called minor compactions all the time in the background, and then it has to do these major compactions that, if you're talking about a multi-terabyte database, can be pretty expensive. They can take minutes or even hours. We've actually offloaded the compaction to be a Spark job now. So it actually removes that concern with using HBase for applications that really require very tight SLAs on response times 24/7. We feel that we by far have the best data loading throughput. We have a fully parallelized bulk loader of our data. You just drop a file on an HDFS directory. We automatically break it up into pieces, do the loading in parallel across the nodes of the cluster, and are able to get extremely high throughput on data ingest. We feel that's a real strength of our system. Someone asked about TPC benchmarks. We actually have run side-by-side tests on TPC-H against these technologies. A lot of them, a lot of the queries won't even run successfully. These are actually JIRAs on queries that did not run, and on ones that we were able to run, we were really significantly faster on comparable hardware. Lastly, if anybody's an Oracle user, developer in the crowd, this is a new thing that we're just coming out with now that we're very excited about, which is native PLSQL support. As I mentioned, a lot of our projects have been ports of Oracle applications, and porting from any SQL database to any other is never as easy as just pushing a button, of course. But we're really trying to make doing that as smooth as possible. One area that we saw was a concern of people that had applications with lots of procedural code, lots of PLSQL. Basically they have natively we had stored procedures written in Java in Splice Machine. So we're now delivered a compiler for PLSQL that has excellent coverage of PLSQL features, so that you can run your essentially Oracle stored procedures directly on Splice Machine. So that's pretty much it. I won't go in, there's a few marketing slides at the end. A key thing I just mentioned is that because we're ANSI-SQL, a lot of standard out-of-the-box SQL tools can just run on Splice machines. So BI tools and SQL tools like you see here. It's easy to integrate with popular modern development environments, web development environments, and have a great team. These are just some key advisors on our company I mentioned. Mike Franklin is really the main person behind Spark. Roger Bamford, who's known as the father of Oracle RAC. Ken Rudin, who now is at Google. He was head of analytics at Facebook. He's now head of search analytics at Google. Great team of people, and we are definitely hiring. So anybody that's interested, please feel free to reach out to us. And then also, I just want to remind you again, it's real, especially now that we've open sourced it. It's very easy to peek under the hood and see what we're doing. You can go here to find out how to get access to the technology and the people in Splice. Yeah, so let me touch on that. It's a good point, because I know I didn't put. We got another minute or two. We good? Okay. The key things that you're looking for in the Lambda architecture, right, are the ability to perform batch operations against really large data sets. Hence the batch layer, where you might be bringing in data on a daily basis or something like that, or you need to run background AI-related jobs, aggregations feature. Like a really exciting area that we see that I think speaks very well to Lambda architecture. Imagine an intelligent application where you have some real-time need to do something based on the results of a machine learning model or something like that that's running against a really large amount of data. But you also need to know the most recent data for it to be effective, right? So this is like a classic thing where you might want a Lambda architecture, right? You have your batch layer where you might be running these big queries that are, say, generating features for your model to run, things like that, lots of aggregation and joins, etc. And then you need to also be able to operate on data that's streaming in. So that's the speed layer. And with Splice Machine, by using a combination of Spark streaming and a message bus like Kafka, again, it doesn't have to be Kafka, you can set up a streaming architecture very easily on top of Splice. Be bringing in that recent data, it'll get stored in HBase, and then when you need to run your heavy-duty jobs, you're able to do that on the Spark engine. So in a sense, it's really, and then when you have to serve the app that's going to do something operationally with that information, HBase is very efficient for being able to do that. You mean like a persistent query? Yeah, I don't think it's something that's native to the database. I can certainly think about ways that you can implement something like that. Yes, right. Yeah, again, that would be a good question if you want to ask in our community. Okay, I know any final burning questions? I think we're probably out of time. I hope this was of interest to folks and at kind of the right level of detail and nice place to stay out of the rain for a couple of hours.
All right, Eric will be, thank you, Eric Kalabacos, VP of Solutions for Splice Machine. Eric will be here for one-on-one questions. Feel free right now, come up and ask him. Thank you all for coming.